All right, chapter 3, day 3 of bivariate data, least squares regression line. This is a long video. I'll try to explain as good as I can. I'll use my calculator. On the answer key that you may be looking at, part of it has some couple of things that I don't like how he did it, so I'm going to go to a blank one and do it over again. So let's run through this. Let's see here. So least squares regression line, it has many also known as the regression line, line of best fit, all kind of the same thing. It's labeled Y hat. Hat, the label hat means prediction. So predicted Y is what that symbol means with a hat on. Think of a predictor like a horse race truck. He's got a hat on to predict who's going to win the horse race. The key properties of this, it always contains the point X bar, Y bar, which is pretty cool. So the averages of the X and the averages of the Y is always on that line, okay? The Y-intercept is A, and the interpretation of that is you'll have to, we'll practice this a little bit, but it's the prediction when the value of X is 0. Sometimes the value of X is unrealistic in the problem because it doesn't fit the domain of the problem. For example, if you did like a height weight thing, like you weigh a certain amount for height, the Y-intercept would make no sense because the height of someone is never 0. So sometimes it makes sense, sometimes it doesn't, depending on the realistic domain of the problem. Okay, so keep that in mind. The slope, this is the formula for the slope. This comes up usually in multiple choice. They'll give you 3 of the 4 and you got to solve for the 4th. You'll see slope you guys are familiar with because slope is rise over run or y over x. In trigonometry, slope is tangent, and tangent is sine over cosine, which is y over x. So you're familiar with that. This is a hybrid of that one, or another knockoff of that formula. Okay. The interpretation of slope, it's a for every problem. So start with the word for every. That's a sentence frame for you. For every increase in y, increase of x, y is predicted to increase or decrease depending on if the slope is positive or negative. Okay. Keep in mind when the slope is negative, r is negative. When the slope is positive, r is positive. So that's another thing to keep in mind. And a couple other things about the key properties. The job of the least squares line is to minimize the sum of the squared residuals, which is that vertical gap between what actually happened, the observed values, and what's predicted to happen with the line. And the residuals actually always add to 0. If you add up all the positive ones on top of the line and all the negative ones below the line, let me draw that real quick. You got some points here like this. You got some points here like this. All of the positive ones and all of the negative ones will actually add to 0. That's why we square them all to get a value, and then we try to minimize that value. Okay. Common misinterpretations. Causation is not implied on the least squares regression line unless it's an experiment. Then you can imply causation. It's just a relationship you're trying to establish, and these are predictions only. Actual outcomes may vary. Okay, predictions only. Okay, you've heard that on commercials before. All right. There we go. Use the given least squares regression model to answer the following questions. Here we go. So the slope is, in this case, is 12,000. So the interpretation is for every GPA point increase in GPA, the income is predicted to increase by 12,000. Okay. Try to get the word predicted in there in your sentence frame. Okay. It's a for every X increase or decrease in Y, but you got to massage the English language to make it sound correct. Let's interpret the Y-intercept. Is this realistic? Can you have a GPA of 0? I think you can. Okay. So the predicted income for a 0.0 GPA is $20,000. Great. And find the predicted value for a GPA of 3.8. So just put 3.8 in for this and multiply it by 12,000. You can do that on your own very easily and add 20,000 and you'll get 65,000. Take the time to do that, pause the video, etc. Okay, 1B, made up problem. Errors on a test, just some random test. I've noticed that the longer you take on the test, the better you do. So there's 8 predicted errors minus 0.2 times how many minutes you spent. So interpret the slope. For every increase of 1 minute spent on a test, the number of errors is predicted to decrease by 0.2. Okay, again, predicted. Get that word in there. Start the sentence frame with for every. Okay, interpret the y-intercept. Can you spend 0 minutes on a test? That may be unrealistic, but it may not if you consider somebody that took a multiple choice test and just marked C in 10 seconds. They effectively spent no minutes on the test. Okay. The predicted number of errors for 0 minutes on the test is 8. Maybe there's only 8 questions, so you'd make all the errors, something like that. Again, this is just a real simple problem that I didn't get too deep into. Find the predicted value for someone who spent 40 minutes on a test. So take 40, put it in for that, multiply it by 0.2. I think 0.2 times 40 is actually 8. 8 minus 8 is 0. So the predicted is 0. Okay. Then I got a cool little problem here about how fast you drive on average. Accidents in a lifetime is 1 plus 0.3 times the average miles per hour. So for every increase of 1 miles per hour, the number of accidents is predicted to increase by 0.3. Okay. And then the y-intercept, if you don't drive at all, I mean, is that realistic if you don't drive at all? Maybe for an individual car, if it's just a classic that's parked in front of your house, you could still have an accident. I guess it could get hit by another car, I guess, but it kind of lacks a little realism. Okay, that might be extrapolation. And then find the predicted value for someone who averages 80 miles per hour. So put 80 in for that. So 80 times 0.3 is, I think, 24 plus 1, 25. That's a lot of accidents in a lifetime. Okay. Next part, I'm going to switch over to a blank thing in a second here, but let's look at just this part. What is a residual? So if you look at this, again, let's just draw a prediction line and some points. Okay. Let's say these are my points. So the residual, and if there's one on the line, that has a residual of 0 because it's right on the line. So what a residual is an error. Okay, errors are weird words. It's not like you did anything wrong. It's just it didn't hit the line. Okay, it's algebraically it's y minus y hat. Y is the observed or actual point, and y hat is the predicted point. And this is not p hat, y hat. Okay, y hat. Just put this on your paper, y hat. Don't put, I spelled the word out, but don't do that. So graphically, it's this vertical distance right here. That's called a residual, the vertical distance. Okay, so I'm going to go to a blank one now. And after I do this, a positive residual, let me go back over that drawing here. A positive residual is these ones above the line. So when the actual value is bigger than the predicted value, okay? And what that means is the line actually under-predicted the outcome, okay? A negative residual means it's below the line, like right here, below the line, okay? Where the actual value is less than the predicted value, and that's an underperformance, okay? You could say the line over-predicted. It's kind of weird to have a negative residual and the line over-predicted. So sometimes over goes with negative. You got to kind of get used to that. Okay. At this point, write that down. That'll help you. Now I'm going to go to a blank one here, okay? And we're going to work through these problems. They're not hard, but I've found over the years, kids can sometimes struggle with these, okay? But they're not hard. So let's just play with this idea of residual. I'm going to write that formula back up here again. So y minus y hat equals residual. I don't know of a symbol for residual. It's not R, that's something else. I'll have to write the word out. Y minus y hat is the residual. Okay, so let's try this. Here's our equation from above. The observed value of GPA was 3.1. 3.1 was 62,000. What was the residual? All right, so you got this coordinate of 3.1 comma 62,000. I'm going to figure out what the line predicted your GPA would be by putting 3.1 in for GPA. So let's try that. 3.1 in for GPA. Got to kind of memorize the formula here. So I'm going to go, what's it again? 20,000. Yeah, 20,000. So it's 20,000, 20,000 plus 12,000 times 3.1. This is the predicted value. This is Y hat, 57,200. Okay, so I'm going to write this out. So to get the residual, I'm going to go Y, which is 62,000, minus Y hat, which was, what did I say here? It was, I think, 57,200. 57,200. All right. Minus 57,200. That's going to be my residual. So you got something like this where this line is right here, correct? And this point is above the line. Okay, so this point is 57,200. This point is 62,000. So the residual is positive, meaning the line under predicted it, or there's an overperformance of the point. And I believe you subtract that, it sounds like 4,800, I think is the answer. That's the residual. Okay. Then the next problem goes the other way. The residual of 3.5 is 2,000. What was the observed value? Observed value is Y. So Y minus Y hat equals negative 2,000. So I have a situation now where I have a line and I got a negative residual, so it's below the line. Okay. So I got to fill that in. The observed value is Y. I can get Y hat by putting 3.5 in for this equation. So let's go ahead and do that, okay? Okay, here we go. So it's going to be 20,000 plus 12,000 times 3.5. Does that sound right? Yeah, so no, I put 2,000. I did something wrong. 20,000. My bad. 20,000. Get the right numbers. Plus 12,000. This is like live here, television here. Times 3.5. 62,000. Okay. Whew. 62,000 is the predicted value. Okay. So it's going to be what? It's going to be Y minus 62,000 equals negative 2,000. Then use algebra and you'll figure out pretty quickly that Y is 60,000. Okay. Because 60,000 minus 62,000 is negative 2,000. That's the observed value, or Y. Observed value and actual value are the same thing. They mean Y. Okay. Let's go to 2B. Errors. Okay, we've seen that problem before. The observed value for 135-minute standard test was 2. What was the residual? Okay. The observed value for 35 minutes was 2. Okay. What was the residual? Okay. So again, the formula for residual is Y minus Y hat. Okay. Equals the residual. Okay. And they tell me the observed value was 2. So 2 minus Y hat equals R. So what I have to do is I got to find Y hat first and then plug it into this equation that I'm checking. Check. And then I will get the residual. Okay. So I'm going to put 35 in for this. So let's do it up here. 8 minus 0.2 times 35. I believe that 8 minus 0.2 times 35 is 1. So that's 1. So I'm going to put that in here. So 2 minus 1, that's y hat equals r. So the residual was 1. So the residual is just barely above the line, right about there. Below the residual of 1. Okay. The next problem does the reverse. The residual for 1 10-minute spent on a test was 3. What was the observed value? Observed value is y. Okay, so what's the observed value? Y minus y hat equals residual was 3. Okay, so I'm going to put 10 in for here. Okay, so 8 minus 0.2 times 10. Okay, so 8 minus 0.2 times 10 is 6, right? Because 0.2 times 10 is 2. 8 minus 2 is 6. So now I'm going to go y minus 6 equals 3. And use it equals 3. Put the answer there. If you do a little algebra, add 6 to both sides, y is going to equal 9. Okay, so the observed value, or y, is 9. Okay. This next one, I think on the answer key, be careful if you look at it without the video. I think the answer key is wrong. Sorry. Okay, so accidents in a lifetime, the observed value was 2. What's the residual? I think it says a giant residual. So I'm going to go ahead and put in 67 times 0.3 plus 1. All right, so let's go to this. Let's get y hat. So 67 times 0.3 plus 1. 21.1. Okay. Wow, that's a big prediction. 21.91. Okay. So the observed value was 2. That's why 2 minus 21.1 equals the residual. That's a giant residual. So 2 minus 21.1, I believe, is negative 19.1. Wow. So that's the prediction's way off. Sometimes you have points that are super far apart, and you get a line that's they develop it by technology, but it's way off. Okay. All right. Then the residual for 134 miles per hour was -2. What was the observed value? Okay. So the residual was -2. All right. So I'm going to put in 34 for this. Okay. So let's try to get that answer. Okay. So I'm going to go 34 times 0.3 plus 1. So I got 10.3. Okay. So I got 10.3. All right. So the residual was -2. Okay. The observed value is y. And then what did I get again for the y hat? I did it right here in the calculator. Y hat was 10.3. Yeah, 10.3. All right. Let's see here. So what minus 10.3 is -2? I believe that's maybe 8.3. 8.3 minus 10.3 is -2. The observed value. It's kind of a weird observed value because you don't have a 0.3 accident, but it's just a made up problem. I hope you understand the math on that. Okay. If that last one baffles you, don't worry about it. Just try to get some examples in there. Okay. We're going to work with this many more days. All right. So I'm going to flip back over to the answer key. Like I said, I didn't like how I did this. First of all, I put P hat instead of Y hat. I made some mistakes on that. All right. Let's look at residuals differently. Okay. There's something called a residual plot. You would never have to make it on the AP test, but you may have to analyze it. And it's really strange. I don't think it's really that necessary for linear data, but for some reason they've stuck with it. It has a little more value when you have nonlinear data, but we're not studying nonlinear data till chapter 12. Okay. So here's the deal. It's really easy to make a residual plot. The residual plot, what it does, it's really simple, but it's worth going through here. What the residual plot does is it takes the trend. In this case, this purple line is the trend, which is the line. And this chapter is always a line. And what it does is it takes that trend, okay, and it turns it on its side, okay? So it just takes this and makes it horizontal. Then what it does is it takes every point, like this point right here is 2 units above the line, and it puts this 2 units above the line. Then it takes this one and puts it 1 unit below the line. Then this is 1 unit above, so that's 1 unit above. This is 1 unit below, that's 1 unit below, etc. And what it does is it makes a little plot here. Now there's a term. There's many terms, but I call it randomly scattered. You may want to write this word down. Randomly scattered. Okay. So if the residual plot is randomly scattered, meaning there's half above the line, half below the line, and they're all pretty close to the line, no pattern, then the line is thought to be a good fit for the data. It's part of the analysis process. The question may be, is the line a good fit for the data? How do you know? If the residual plot is available, you would say the residual plot is randomly scattered and has no pattern. So therefore, I think the line's a good fit for the data. Okay, that's kind of the idea. So let's look at the next one. Okay, so let me make this a little smaller so I can get it in there. Okay, so let's look at this one. Okay, this one, I give you the residual plot, which looks really beautiful. It's randomly scattered, and you're going to go ahead and make the trend. Okay, and so this I put the line here, then you got to make the trend. Okay, so if you're working on this on your own, you could shut the computer off or whatever, but this is 1 unit above, so I would go 1 unit above right here. This is 2 units below, I would go 2 units below. This is right on the line, so that's right on the line. This is 2 units below, so that's 2 units below, etc. Couple things. Remember, in theory, not in theory, but it's a fact, I should say, the least squares regression line zeroes out the sum of residuals. So all of these positive residuals and all of these negative residuals are zeroed out. They're made to be 0. Okay, in this situation. Okay, and they're all of these. All right, now check this out. The third one, this residual plot is not randomly scattered. It's not. If you went back and you went ahead and made this pattern right here, you would see that a line doesn't explain the data. Now, what's ironic or obvious is if you had this plot only, it doesn't even pass the eyeball test. A line is clearly not a good fit for the data. This is like a parabola or something else, but we're not studying that right now. All we're doing in chapter 3 is determining, is a line a good fit for the data or is it not? So the residual plot here, it shows a pattern, but this showed a pattern too. Okay, so that's why the residual plot is kind of a weird concept that we hold on to in old school stats, but it's okay. We're just learning it. All right. So the question becomes, when is it appropriate to use a linear model? Okay. So there's something in the book, they call it the straight enough condition in the book. It's just the eyeball test. Does it look relatively linear? Yes or no? You don't want some crazy outlier that makes it look artificially good or bad. Because remember, an outlier that's right on the line increases R. An outlier that's way off the line decreases R a lot too. So you got to be careful. And you want that residual plot, if it's shown to be randomly scattered. It's not always shown on a prompt. Okay. So let's go ahead and look at this. And we're going to go back to this. The question is right here. Would it be appropriate to use a linear model of the data for the following graphs? Okay, that's the question. Okay. And the answer is Yes, on 2D, absolutely. This plot looks randomly scattered. The data looks relatively linear. Okay. On this one as well, yes, the plot looks randomly scattered. But on F, no. The plot doesn't look linear to begin with, and the residual plot shows a definite pattern, so no. Now, if you had these down here, okay, how about this one? If this is the residual plot, is that any good? No. This definitely shows a pattern right here. It's not randomly scattered, half above, half below the line. How about this one? This is also no. It's got some weird pattern here. It's not really randomly scattered. There's all kinds of patterns. This is the one you want for the residual plot. Looks randomly scattered, no pattern. When I say pattern, don't look for like an elephant, like your cloud watching or something. Just, it just, half above the line, half below the line. The closer to the line, the better. Okay. So there is a look at all of this. I think that's pretty good. So that is chapter 3, day 3. I hope you enjoyed that.